Welcome. By the time you leave this session, you will be able to do three things: verify that a fitted factorial model is trustworthy, read the right plot to identify optimal factor settings, and translate both of those steps into a concrete, defensible recommendation for a client or a process team. Those are the skills that close an experiment, and they are what we cover today. Think about where we are in the analysis workflow. We have run the experiment, estimated the effects, and reduced the model by dropping terms that were not significant. That is estimation. But estimation alone is not enough. Before you hand anyone a recommendation, you need to answer two questions. First, is the model adequate? Can we actually trust the surface it describes? Second, given that surface, what factor settings should the client use? Adequacy comes first, because a recommendation built on a flawed model is worse than no recommendation at all. Let me set the stage for our running example. A chemical engineer ran a replicated 2 to the 3 factorial experiment to maximize product yield. The three process factors were reaction temperature at 160 and 180 degrees Celsius, catalyst concentration at 2 and 4%, and stirring speed at 200 and 400 revolutions per minute. Each of the 8 corners of the design was replicated 3 times, giving 24 runs in total. After screening all 7 estimable effects, the reduced model retained temperature, catalyst concentration, and their two-way interaction. Stirring speed was dropped. It was not significant. That reduced model is what we will now diagnose and then use to make a recommendation. Before we diagnose anything, let us make sure the data structure is clear. The first 8 rows of the 24-run table show the pattern. Run 1 through 3 are all at 160 degrees, 2% catalyst, 200 RPM, the low corner, and the 3 measured yields are 61.3, 59.8, and 60.5%. The fitted value for all 3 of those runs is 62.3% because the model predicts the same value at every replicate of the same corner. The residuals are negative 0.98, negative 2.53, and negative 1.79, the difference between what was observed and what the model predicts. Runs 4 through 6 shift stirring to 400 RPM but keep temperature and catalyst the same. Yields are 64.3, 64.1, and 63.7, all fitted at 62.3 with positive residuals. Runs 7 and 8 move catalyst to 4% at 160 degrees, and the fitted value jumps to 66.2, but the observed yields of 59.7 and 58.4 fall well below that, giving large negative residuals. Those residuals are the raw material for everything that follows. Residual diagnostics are not a formality. They are the mechanism by which you check whether the assumptions baked into your model are consistent with the data you actually collected. We use 4 standard plots, each targeting one assumption. The plot of residuals against fitted values checks for constant variance. You want a horizontal band of roughly equal width, with no fanning out as fitted values increase. The plot of residuals against run order checks independence. You want no systematic drift or trend across time. The normal probability plot checks whether the errors are approximately normally distributed. You want the points to track the diagonal reference line. And residuals plotted against individual factor levels or groups check for any remaining structure the model has not captured. A clean plot means no evidence against that assumption, not proof of perfection, but no red flags. Here is a caution that experienced analysts know, but beginners often miss. With 24 observations and only a handful of distinct fitted values, residual plots will not look as smooth as textbook examples. A normal probability plot with 24 points will have some wobble. 1 or 2 points that stray slightly from the diagonal are expected by chance alone. What you are looking for is systematic departure. A consistent curve, a clear fan, a monotone trend across run order. Isolated wiggles are noise. Consistent repeating patterns are signal. Keep that distinction in mind as we look at the yield model diagnostics. We now apply all 4 diagnostic plots to the residuals from the reduced yield model. The task is to assess whether any of the 4 standard assumptions, constant variance, independence, normality, and homogeneity across factor levels, shows evidence of violation. Looking at the 4 panels together, the picture is reassuring. In the residuals versus fitted plot, the points scatter randomly around 0 at both clusters of fitted values. There is no fan shape, no systematic widening, so constant variance is plausible. In the run order plot, there is no upward or downward drift across the 24 runs. The process was stable throughout the experiment. The normal probability plot shows the points tracking the diagonal closely, which is about as good as you can expect with 24 observations. Normality is plausible. And when residuals are examined by temperature level, the spread at 160 degrees and at 180 degrees looks comparable. No evidence of heterogeneous variance across temperature groups. Taken together, these 4 plots raise no concerns. We can proceed to the formal test of model adequacy with confidence that the basic assumptions are not being violated. Now we move to the formal test of model adequacy, the lack of fit test. This test is only possible because we have replication. Here is the key idea. The total residual sum of squares from the fitted model can be split into 2 pieces. The first piece is purge. This is the variation among replicates at the same corner of the design. Because those replicates share identical factor settings, any difference between them must be random noise. Pure error is model-free. It does not depend on what model you fit. The second piece is lack of fit. This measures how well the corner means predicted by the model. Match the observed corner means. If the model form is correct, those 2 quantities should agree within the noise level. The partition is residual sum of squares equals pure error sum of squares plus lack of fit sum of squares. This decomposition is the payoff for replicating your design. The lack of fit F statistic is the ratio of the lack of fit mean square to the pure error mean square. If the model form is correct, both mean squares estimate the same underlying noise variance, and their ratio should be close to 1. A large F. One that exceeds the critical value tells you the model is missing something structural, perhaps a dropped interaction, perhaps curvature that a 2-level design cannot detect. A non-significant F tells you that, given the precision of your replication, there is no detectable deficiency in the model form. One important nuance: a non-significant loft test does not mean the model is perfect. It means replication cannot detect a problem. If your replicates are very noisy, the test has low power. Adequacy, in this context, means the fitted form is consistent with the data, not that it captures every nuance of the true response surface. We now apply the lack of fit partition to the reduced yield model. The residual sum of squares from the fitted model will be split into its pure error and lack of fit components. We then form the F ratio and compare it to the appropriate critical value to decide whether the model form is adequate. The lack of fit F statistic for the yield model is small, and the associated p-value is well above any conventional threshold, certainly above 0.05 and well above 0.1. What does that tell us? The corner means predicted by the reduced model are consistent with the observed corner means within the noise measured by pure error. There is no statistical evidence that the model is missing a structural term. Now, what would we do if the F were large and significant? We would first suspect a dropped interaction. Perhaps stirring does interact with one of the other factors in a way the initial screening missed. We might also consider adding center points to probe whether there is curvature in the response surface that a two-level design cannot capture, and we would flag the limitation clearly to the client before making any recommendation. But in this case, none of that is needed. The model passes the adequacy test. With adequacy established, return to the recommendation. And here is a rule that practitioners sometimes get wrong. When an interaction is active, you must never read the optimal level of an interacting factor from its main effect plot. A main effect plot for temperature averages the yield over both levels of catalyst. That average can hide a crossover, or it can understate how much the optimal temperature depends on which catalyst level you are using. The correct approach is to read factor settings from the highest order significant term that contains those factors. In our case, that is the temperature by catalyst interaction plot. An interaction plot works as follows. You put one factor on the horizontal axis, say temperature, and you draw one line for each level of the other factor. In our case, one line for 2% catalyst and one line for 4% catalyst. Each point on a line is the mean response at that combination of the two factors. If the lines are parallel, the effective temperature is the same regardless of catalyst level, and there is no interaction. If the lines are not parallel, if they converge, diverge, or cross, the effective temperature depends on catalyst level and an interaction is present. The optimal corner is simply the highest point on the plot if you are maximizing, or the lowest point if you are minimizing. For factors that do not appear in any significant interaction, the inactive factors, you set them at whatever level is cheapest, safest, or most convenient for operations. We now build the temperature by catalyst interaction plot for the yield experiment. We use the model predictions at each of the four corners defined by the two active factors, and we overlay the observed corner means to check how well the model tracks the data. The interaction plot tells a clear story. The two lines are not parallel. Catalyst concentration amplifies the effect of temperature. At 4% catalyst, yield rises sharply as temperature increases from 160 to 180 degrees Celsius. At 2% catalyst, the gain from increasing temperature is much smaller. The optimal corner is therefore 180 degrees with 4% catalyst. That is the highest point on the plot. The open circles, which represent the observed corner means, sit very close to the model predictions at every corner. That visual agreement is entirely consistent with the clean lack of fit test we just saw. Notice what a main effect plot for temperature alone would have shown, a positive slope, averaged over both catalyst levels. It would have told you to use high temperature, which is correct, but it would have completely hidden how much of that gain depends on pairing high temperature with high catalyst. The interaction plot gives you the full picture. The recommendation from this experiment is concrete and defensible. Run at 180 degrees Celsius with 4% catalyst. Those are the two active factors, and both should be held at their high levels based on the interaction plot. Stirring speed was inactive. It had no detectable effect on yield across the range tested. That means the client can choose whichever stirring level is cheaper to operate, easier to maintain, or safer for the process, without any penalty to yield. That finding about stirring speed is not a null result to be dismissed. It is actionable information. The experiment has just told the process team that they have a degree of freedom in their operating conditions, and that is exactly the kind of practical output that justifies running a design experiment in the first place. Let us consolidate the key findings from the yield experiment before moving to practice. On the diagnostic side, residual plots showed stable variance, no run order drift, and near normal errors. All four assumptions held. The lack of fit test was non-significant. confirming that the reduced model is structurally adequate. And critically, replication was what made the lack of fit test possible at all. Without those 3 replicates per corner, we would have had no pure error baseline and no formal test of adequacy. That is a key design dividend, one more reason to replicate when resources allow. On the recommendation side, the optimal settings are 180 degrees Celsius and 4% catalyst, with stirring speed free to be set on operational grounds. The interaction between temperature and catalyst is what drives the recommendation. Reading main effects alone would have given an incomplete and potentially misleading picture, and the finding that stirring is inactive flags a genuine cost or safety opportunity for the client. Those are the 2 deliverables from a well-executed factorial experiment, a trusted model and a clear justified recommendation. Now it is your turn to work through the same sequence on a new dataset. The coating thickness experiment is a replicated 2 to the 3 factorial on a coating process. The 3 factors are cure temperature at 150 and 200 degrees Celsius, coating speed at 10 and 20 meters per minute, and primer type, either A or B. The response is coating thickness in microns, and the goal is to minimize thickness. There are 2 replicates per corner, giving 16 runs in total. After screening, the reduced model retains coating speed and the temperature by primer interaction. Cure temperature and primer type are both active through that interaction. Coating speed is active as a main effect, and the remaining terms were dropped. Here is the full 16-run dataset. Each of the 8 corners has exactly 2 replicates. At 150 degrees, 10 meters per minute, primer A, the 2 thickness measurements are 42.1 and 41.8 microns. Switching to primer B at the same temperature and speed drops thickness to 38.5 and 38.9. Moving to 20 meters per minute at 150 degrees with primer A gives 35.2 and 35.6, with primer B 31.8 and 32.1. At 200 degrees 10 meters per minute, primer A gives 38.4 and 38.0. Primer B gives 34.9 and 35.3. And at 200 degrees 20 meters per minute, primer A gives 44.1 and 43.7. Primer B gives 40.5 and 40.9. Notice that pattern at 200 degrees and 20 meters per minute. Thickness is higher there than at lower speed. That is a hint that something interesting is happening with the interactions. Keep it in mind as you work through the diagnostics. Your first task is to fit the reduced model, extract the residuals, and produce the 4 standard diagnostic plots. As you examine each plot, ask the same 4 questions we asked for the yield experiment. Is the variance constant across fitted values? Is there any drift in run order? Do the points track the diagonal on the normal probability plot? And is the spread comparable across factor groups? The diagnostic plots for the coating thickness model are clean. Residuals versus fitted values show a tight symmetric band with no fanning. Constant variance holds. The run order plot is flat with no trend. The process was stable across all 16 runs. The normal probability plot tracks the diagonal closely, which is reasonable for 16 observations. And when residuals are examined by primer type, the spread for primer A and primer B looks comparable. No evidence of heterogeneous variance by primer. No concerns to report from the diagnostics. We can proceed to the formal adequacy test. Now partition the residual sum of squares into pure error and lack of fit for the coating thickness model. With 2 replicates per corner, you have 8 pure error degrees of freedom, 1 per corner. The lack of fit degrees of freedom are whatever remains after accounting for the model terms. Form the F ratio of the lack of fit mean square to the pure error mean square, and assess whether the model form is adequate. The lack of fit F statistic for the coating thickness model is small, and the p-value is large, well above any conventional significance threshold. The interpretation is the same as for the yield experiment. The corner means predicted by the reduced model are consistent with the observed corner means within the noise level established by the two replicates per corner. There is no evidence of a missing structural term. The two replicates per corner are doing exactly what they were designed to do, providing an honest, model-free estimate of pure error that allows us to formally test whether the model form is adequate. The model passes with adequacy confirmed. The final step is to build the temperature by primer interaction plot. Use the model predictions at each of the four corners defined by cure temperature and primer type. Remember, the goal is to minimize coating thickness, so you are looking for the lowest point on the plot, not the highest. The interaction plot for the coating thickness experiment reveals a crossover. The lines actually cross. At 150 degrees Celsius, primer B gives lower thickness than primer A, but at 200 degrees, primer B gives higher thickness than primer A. This is a true crossover interaction, and it is exactly the situation where a main effect plot for temperature would be completely misleading. Averaged over both primers, temperature would appear to have almost no effect. The gains at one primer level cancel the losses at the other. The correct recommendation is 150 degrees Celsius with primer B. That is the corner that minimizes coating thickness. Coating speed was active as a main effect. Higher speed reduces thickness. So the recommendation should also specify the higher speed level of 20 meters per minute. And because coating speed appears only as a main effect and not in an interaction, its direction is consistent regardless of the other factor settings. As for the practical bonus, the experiment has confirmed that the choice between primer types matters enormously at high temperature, and that running at low temperature with primer B is the path to minimum thickness. That is a clear, justified, and actionable recommendation, exactly what a well-designed experiment should deliver.